Okay. Last time we were talking about, we were solving the previous homework assignment, but in terms of lets, right? Trying to understand some of the limitations of lets and also, the advantages of lets. Because if we look at our previous homework assignment, the real issue, the difficult part of that assignment was the fact that we needed to remember something about our first call before we can make that second recursive call, right? Because it was important what we were kind of left with. So the thing we were working with was the thing that the div list stuff, flippy dealy things, right? I had you read ahead a little bit for the let expressions we'll look at here today. But so we were looking at these things, the diff expressions. So the issue is that we don't necessarily know how deep a diff expression is going to go. So we kind of have to follow the breadcrumbs down that until we get to our final answer, until we finally finish getting the full diff expression. And not until that point would we even be capable of making our second call to whatever we named our function for processing this stuff, because it's effectively a parser, right? So not until that point are we even able to make that call. But we even still had to play a trick then, because what we did is we had a to list, right? The to list had, the first part of it was kind of our answer from that. The second part of it was what's left. And that what's left piece is what we're going to use to pass in to the next one. That's the guy that we really needed to know about before we can make our second recursive call. Okay, so we decided we implement this as with some lets. So if we kind of go through this, so here's our parsed list o stuff dealy flippy thingy, and actually no, this was for the homework assignment. So we just started. So for the parse, what do we call this guy? We didn't even write the parse piece yet. So we wrote this function called get next prefix expression. So if I were to pass a prefix expression to this guy, it will then give me the next one as a to list. Right? That's what this dude gives me. He gives me a to list, which has the first part of it is the next prefix expression, and the catter is everything left after I've extracted that prefix expression. Those two pieces. Okay? So as we come through here, if we're looking at the empty list, just return the empty list for now. If I'm looking at the number, this was our easy production of this guy. So if I'm looking at a number prefix expression, great. What do we do with the number? We go ahead and we create a list whose first element is that number and whose second element is the rest of the prefix list. That's the to list I'll produce under that situation. Okay, no more recursive calls there. Otherwise, I must be in the difficult, the diff prefix or whatever we called it. All right, so in that case, I care about a couple of different things here. So I created a nested let. Why do I need a let inside of a let? Just to review kind of what I mentioned last time about let expressions. We talked about two different kinds of lets. We talked about a let and we talked about a let star. I probably mentioned the third one called a let rec as well, but don't worry about that right now. What's really the difference between a let and a let star? And why did I use two separate lets here? Man, this is just really nice build quality, seriously. I mean, it's made of like brushed aluminum. It's just really nice. Why couldn't I have put both of these name value pairs inside of a single let? Why did I need a let inside of a let? What's the weakness of a let? No, you can have 50 variables inside of a let. Does nobody really know the answer? Somebody has to. We mentioned it last time. In this second let here, I'm defining result 2 in terms of what? In terms of result. So result 2 needs the answer of result in order to work. A let does not allow you to define variables in terms of other variables defined in the let, even if they were defined before this. Does that make sense? Why do you think that is? Well, we're going to find out here pretty soon when we go to write it, because that's what you read forward to, right? You started seeing that we have a language now that includes a let. If you're implementing a let, when you go across there and you create those variable value pairs, isn't the easiest implementation of that to deal with each of those individually and they don't necessarily know about each other? So when you get the value of result here, you're kind of getting the value of result 2 simultaneously. You didn't wait for the answer to this one before you got the answer of this one. You made the 2 different recursive calls yourself. So because you wanted the implementation to be easier, that was a limitation on what it could do. So then they have a let star that says, well, we'll make the implementation of let star a little bit more difficult. That way, it actually allows you to have variables defined in terms of other variables within the same let. So what we had to do is we had to build our own thing. We said, here's the outer let. Go ahead and give me the value of result. And then in the body of that let, we'll go ahead and define another variable called result 2. And now I'm allowed to do that guy in terms of the value of result because I have the value of result at this point. So having a let inside of a let in this case allowed us to accomplish something similar to having a let star. That makes sense? And then that final step, which we're not going to talk about for a little bit now, actually, is the let rec. Does anybody remember what I said about let rec? I probably didn't make a big deal about it, so it's pretty probable that if you didn't remember what I said Friday about this guy, that the let rec is gone. Let rec supports recursion. So I can actually make recursive calls to functions within the let. And that allows you to define a function in a let and actually recursively call that function within the let. That's advantageous because that really helps you not having to have all these extra helper functions. Okay? At the cost of your scheme procedure looking scarier. All right, so what we're going to do first here is we're going to have a let, we're going to get one variable, a variable called result. Now, don't let this confuse it because this is not the situation like you pointed out. We're not limited to one variable. We can have 50 variables inside of a let. They just can't be defined in terms of each other. We can't say A equals 5, B equals A. We're not allowed to do that. But we can say A equals 5, B equals 7. Perfectly legal. Make sense? Everybody understand the difference between those? Okay. So if you were writing a code, why would you ever use a let instead of a let star? Isn't let star better? Isn't it more flexible?
What does let star do again?
Let star allows you, let star would have let me say let A equal 7, let B equal A.
Oh.
Let star lets you do that, lets you define B in terms of another variable you've defined inside that let. Where a let would not let you do that. The illegal thing would have been B equals A in a let. Why wouldn't you just use a let star all the time?
It's more costly, right?
Yeah, potentially for performance reasons, right? We might say, okay, well, we didn't actually write it, but it wouldn't take a whole lot of thought for us to decide that a let star is probably more complex than a let in terms of its implementation. Therefore, it's doing some extra work. And if we don't need it to do that extra work, that's okay. Now, do we care about that as programmers? Go ahead.
Yeah. I mean, yeah, but what would that look like with the let star then? How would the syntax be done?
Oh, if I was writing this as a let star,
Yeah.
this would just be called let star. And inside of this opening and closing parenthesis for the body, I would just have this second one here just in there.
Okay.
So I'd have this guy just sitting inside that list of name value pairs. Is this all of them? There to there. It would look like that. So you'd have a let star with a list of varied name value pairs, and in that list you'd have result, and you'd have result 2, and result 2 is defined in terms of result.
So in any let, we can have multiple variables, and let star we can define variables in terms of other lets, and then in let rec we can use reverse, or we can use.
Okay, well, the second part of that, in a let star, you can define variables within the let star in terms of other variables that were also defined in that same let star. Yeah, because here we are defining, here we're defining result 2 in terms of result. It just took a second let to pull that off. Yeah, so we built our own let star, right? Who needs it? Now, but we could also then say that the definition of a let is probably complex enough that this is using some extra resources that aren't a big deal. Okay, but realistically, though, do we care as programmers today? Cool kids write their own stuff. Well, so think back to your either your Java or your C#, whatever. We have our primitive types in those languages, right? So what are the primitive types for integers in Java? Come on, people. I'll get you started. Int. But technically, it's not the wrong answer. Char is a primitive. It just happens to be an unsigned integer type. Okay, long. Doubles are floating point types, but it is a primitive type. Short, byte. So we have byte, short, int, long. Those are really our 4 primitive integer types. Why do we have 4 different ways of holding whole numbers that are positive and negative? What's the rationale for that? Yeah, they use different amounts of memory. And that was important way back when that first came about in late 60s with the C programming language. How many of you, when you're writing your Java code today, really pay that much attention to that? It's like, this is only going to hold a number between 1 and 10, so I'll just store that in a byte. I might as well be economical. You don't think about that? Huh? Well, Y2K happened because they were, it's kind of the inverse thing. The whole Y2K problem was that they said, well, we know we have a memory problem. So we're going to go ahead and represent all years as 2 digits. So 1978 was just 78. 88 was 88. 98 was 98. 99 was 99. 2000 was the same thing as 1900. Whoops. we got a problem. That's where so it was kind of the inverse issue there. Today, we just don't, today we would store a 4-digit year as a 12-digit year. Well, okay, but why don't we care today? Because memory is not a problem, right? Memory is not a problem today. There's only very specific applications where memory becomes a bottleneck for us. Is that a fair enough statement? Now, that doesn't mean we shouldn't care about it. And it also doesn't mean as a computer scientist we shouldn't understand it. Okay, that's why I kind of harp on those things so much, because one day, maybe, well, here, I'll guarantee this, and this is more of a soothsayer thing, okay? One day, one of you in here, at least, is going to run into a problem where it will make a difference. That's gonna happen, okay? And because you have that computer science background, you understand the theory of it, as we didn't evidence today, you're going to be prepared for that, because you're going to be able to say, what's happening here? We're actually running out of memory. Because of the nature of this program, we are running out of memory. And now I need to do something about that, because I now recognize that's what the problem is. Now, in your world today, your programming world today, so this is more of a trivia question / test of your understanding of what I just said. What would be your best chance? Give me a scenario that would be your best chance of running out of memory. It doesn't have to be a specific scenario. What type of implementation or what type of algorithm would have the best chance of running out of memory in today's, based on what you know as a programmer? Yeah, recursive. I mean, that's going to be your best chance. We could pretty quickly write a little Java program that makes too many recursive calls that'll give you the Stack Overflow exception. But then you could fix that by going out the Java virtual machine and just give more memory to the stack. Because the default amount of memory they give you for the stack is, a little tiny bit of 8 gigs of RAM. Let's give ourselves a 6 gig stack. Break that. So then you write infinite recursion and you'll break that real quick. No harm, no foul. And we'll see why that is. We'll see that when we implement recursion in here, we're going to actually see that recursion is quite expensive. Because you have to put an entire function on hold. You have to kind of pack all that up and say, okay, I'm going to put you on hold because I'm going to need to come back to you later. Does that sound like anything else that you guys have been introduced to in computer science that was expensive? Where we had to unpack something to use it for a little bit and pack it back up and put it to the side to come back and use it again later on? Deals with operating systems. What's the expensive thing with operating systems, specifically with CPU management, that we need to be careful about? Well, it involves I/O. I/O's the reason for this other piece. Yeah, it's context switching. Context switching. So context switching is the idea when a process loads onto the CPU, gets its time, and then has to leave the CPU. We have to pack that up. All right? Recursion is pretty similar in terms of that the amount of work and the size of that data structure we need to hold on to all the current state of a function. Make sense? All right, so in any case, what did we get here to begin with? We set result equal to the to list that we would get from giving it the to list that we would get by calling get next prefix expression on the CDR, the cdr of the prefix list. What assumption have we made right here? We know that if we're in this else that we're dealing with a minus. The car is a minus, correct? So we went ahead and we peeled this minus off. And when we peeled this minus off, we set result equal to get next expression on this guy. Make sense? And what's that going to produce for us? That should produce for us, in this case, a list. Yeah, see, this is kind of where we left out last time because we actually only partially implemented this in here because I've kind of said, well, we don't need to put our expressions, our pieces in here that we're going to ultimately need. Let's just have it give us the next expression. Well, then we're going to have to reprocess that to get our semantic pieces put in there for the parser. But effectively, what this guy is going to say is I'm going to burn past this. Then I'm going to call the prefix, get next prefix expression on that. And result is going to equal that. So result is going to equal get next prefix expression on this because I've now burned past that first minus sign. Well, when I get into that one, what are we going to do? We're going to put that on hold because we're going to say the next version of result. In fact, let me just dump this right now. So this is version 1 of result. Now I'm inside of this guy. He's not the empty list. He's not a number, so he must be in the else. So what am I going to do in that? I'm going to get a new result. So this is the second version of result. It's not result 2 because result 2 is the guy that's in the second let. I haven't even gotten to the second let yet. I haven't gotten to the first second let. So now what's this result going to equal? This result's going to equal get next prefix expression on all that stuff. Okay, so now we've made another call to it. Is the car of this guy a number? It is. So What am I going to get out of this guy? I'm going to get a list containing a 3 and then containing everything that's left over. That guy. That's what gets produced right here. A list containing the car of the thing, which is the 3, and then the cooter, everything else that's in there. So here's my to list. The car of that list is the expression. The catter of that list is what's left. That make sense? So this is what my second result is going to end up being. So now I drop down into result 2. So result 2 is going to equal get next prefix expression on the catter of this guy. So I'm calling get next prefix expression on that dude. And what's that going to produce for me? It's going to produce a list containing a 2, then containing everything else that's in there. Like that. So that's result, and that's result 2. So now I'm into the body of this let. Okay, I'm in the body of this let based on my second call, my second let combo. Okay, so I'm in the body, and what's the body going to do? It's going to create a list. So I'm going to have a list here, and the list is going to have a list in it with a minus with the car of result. Car of result is a 3. And then the car of result 2. Car of result 2 is a 2. So I'm going to create a list. So again, I'm building a to list. The car of that to list is going to be my diff expression guy. So that's the next diff expression I found, minus 3, 2. And then the catter of result 2, which is that guy. So here's my to list. This is the next prefix expression. And this is what's left after I extracted that guy. Does that look pretty accurate based on what I have with the original result? Is that the next prefix expression right there? And is that everything that's left over? Looks all right? Okay, so this is what it's going to boil down to. So ultimately, that first call to result is going to give me that. Make sense? So now I can go ahead and erase those two guys. I have finished. So what I have highlighted right now, just so you can kind of follow this, I am the second recursive call in, right? So I got the result. In order to figure out the first result, I had to make a recursive call. So I put all that on hold, and now I'm into the second one and got to my, this would have been my next let. So there's that inner result. And then the next let after that, here's result 2. And then I finally got an answer from that. So this whole thing right here ultimately gave me my original request for result, which looks like this. And now the scope where those things that I have highlighted right now exist is now gone. Correct? So my original call to result, or attempt to set the value of result, has now completed. So now I'm going to set the value of result 2. Result 2 is going to equal get next prefix expression on catter of result. That is the second element of that guy. Right? That's what's left after I got the first prefix, or the next prefix expression. All right, so is this guy a number? Well, is the list the empty list? No. Is that a number? No. So I'm in the else. So what do I do if I'm in the else? I put that on hold. I'm going to set result. I'll go ahead and I'll burn past the minus, and I'm going to call get next prefix expression on the catter, or the cooter, sorry. So I'm calling it on that guy. And this guy is going to be one of those easy ones, right? So we call back to get next prefix expression. It's not the empty list, but it is a number. So what's this going to produce for us? It's going to produce a list whose car is 4 and whose catter is that guy. Oop. That's the to list that next inner result will be equal to. Then we get to result 2. All right, so this guy finished. Result 2 is going to be get next prefix expression on the catter of that result. So result 2 is going to say, give me the next prefix expression for that dude. All right, so is that guy the empty list? No. Is the car a number? No. So now we're in the else. What do we do in the else? Well, we got another result. Okay, this is the recursive call stuff. And what's that result going to be equal to? Well, I'm going to burn past the minus, and I'm going to say result is equal to get next prefix expression for the cooter of that, which says give me the next prefix expression for that guy. And that's going to be an easy one, right? So it's going to give me the list whose first element is a 12 and whose second element is the list containing a 7. What's left over? Make sense? Then I'm able to get to my result 2. And my result 2 is going to say get next prefix expression for the catter of that. So that is give me next prefix expression for the 7. Which is going to say, okay, well, here's your to list containing a 7 and the empty list. Now I'm in the body of this result 2, this let. And this guy is going to boil down to a list. So there's my list. Containing the first part of the list is going to be a minus, followed by the car of result, which is a 12, followed by the car of result 2, which is a 7. Close that. And then the catter of result 2, which is the empty list. So that's what this inner thing will boil down to, which actually is the result of this result 2. So all this work I did right here was to calculate the value of this. How much did I delete? Okay, now I'm good. Okay, all this work I did down here was to finally calculate the result of this result 2. Which will give me that guy. So far, so good? So then I'm done with those lines. And now I'm in the body of the let. And what do I do in the body of the let? I create a list. First element is a list with a minus. Car of result. Car of result is a 4. Now let me put a comment in front of this. And then the car of result 2 is that list. That's the first part of my to list. The second part of my to list is the catter of result 2, which is the empty list. Like that. So all this stuff right here is the result of result 2 here, right? So I can go through that. So now I'm in my original let body. And what's my result going to be? My result's going to be the list whose first element is a minus. Well, a list containing a minus. And the car of result. The car of result is this guy. And then the car of result 2, which is that guy, followed by the catter of result 2, which is that guy. So that's what that will all boil down to. Right there. So, is that really the right answer? Effectively, it is, right? All the pieces are there. I just needed to go in and change a few little tiny pieces, right? If we look at the result here, does everybody see how we kind of did that with the let inside the let? So ultimately what we have there is all the pieces we need. Okay, now if we look at the answer, I'll go ahead and bring that this guy right here. I'm going to copy this in just for us to investigate for a second. All right, so this is our answer. Well, really the answer is the car of this guy, right? That's our final, the car of that guy. Okay, we'll have to look at what it's going to take to actually extract that last piece, because we're kind of stuck with a to-list thing here at the end. But forget about that. Let's just focus on the inside. We have a diff expression followed by a diff expression followed by a const expression 3, a const expression 2, followed by a diff expression followed by a const expression 4, followed by a diff expression followed by a const expression 12 and a const expression 7. Are all the pieces there? Every single one of them's there, isn't it? What's the one thing that's different here? Go ahead. Yeah, we didn't mark them up. But do we have all the logic that we need? Is it going to be pretty easy to mark them up? So we decided that this guy should be a diff expression. So rather than saying minus here, we'll just say diff expression. All right. And then we have this other dude here called a const expression. And then rather than just returning our number, this guy right here, this is going to be a list containing const expression and the actual number, followed by the rest of it. Now we've marked it up, right? That's what parsing is. That make sense? Okay. So then, at that point, if I replace all these minuses with diff expression and all of these individual numbers with a list that has const expression followed by the number, do I have what I wanted? Okay, so now the very last piece then is to come in here and we're writing a parser, right? So we have parse prefix expression, something like that, except I need to define that. This is going to be a lambda that's going to take, a prefix expression, prefix list, it looks like. And what am I going to do here? I'm going to return the car of get next prefix expression on prefix list. And that will get me my actual answer. Because actually what I was left with at the end was let's see, where am I at with this dude? Well, I was left with that guy. That was my final answer. The car of that guy is the dude I actually want, right? The catter, when the catter's finally the empty list, I'm done with it. We also saw here that our cond up here for the empty list never happened, right? Because of the way we wrote it, we actually could remove this conditional. Because of the way we're calling it, that never occurs. Now, I actually suppose if we wanted to be fully legit with this, I suppose if we're looking at the empty list for this, we actually should probably return the list containing two lists, two empty lists. that protects us from the one way we'd actually get in here, and that's if whoever calls parse prefix expression passes us the empty list. For no good reason other than we will hand them back a to list with 2 empty lists in it, and he'll return the car of that, which is just going to be the empty list, just to make it compatible. That makes sense? So if this, is that guy my original input? Minus, minus, yep, looks like it. Somebody returned a minus?
You gotta make a list.
I gotta make what a list?
Um,
Thank you, thank you. Bad input. Technically, since usually I have Annie checking on this stuff, that I'm guessing that's a fail for the day. Yeah, yeah. So, is this our answer to that, dude? Looks legit enough? Okay. So now, I mean, we didn't change anything from last time. So we actually had the answer last time, right? We just didn't finish walking through the answer last time. So now, would you say that the 2 lets for this one actually was better than the way you implemented it? Well, certainly was easier. Took us a little bit to walk through it because recursion is confusing, right? You know, how many of you feel that you're better at recursion now than you were at the beginning of the semester? Every one of you should have your hand up, right? Unless you felt you were an expert at recursion before. So you see how you're accidentally getting better at something you used to think you sucked at? And then I also promised you what? You're going to get out of this class, you're going to have trouble going back to iterative. it's like, well, how would you solve this recursively? You're going to be stuck in that mode. Okay. So now if we kind of, what's the flip side of this would be to unparse it. And that's not a huge deal at this point, right? You know, that's the easy part of this question. So we could do that the same way with I guess the lets to process it. Okay, so I want to jump ahead a little bit here then. We did the hard part. So I want to go down to chapter 3 here, where we're dealing with a kind of an upgraded language. You know, the book kind of talks about it like it's a brand new language, but really it's an upgrade to our language of lambda calculus expressions. Nothing real new, we just added some more productions to it and they decided to make it sound scarier. All right, so now we have this language of expressions, where we have this dude called a program. Okay, and what's a program? A program is going to be an expression. Well, what's an expression? And what they're giving you here is kind of the pieces you're going to need for a parser. What they want to call it, you'll call this guy a program. You'll call this guy a const expression, a diff expression, a zero expression, an if expression, a var expression, or a let expression. So now we have a whole bunch of different kinds of expressions. All right, so what's a program? A program is an expression, where an expression is either a number or it's a diff expression where you have a minus followed by an expression followed by another expression. So that's kind of our upgrade of our app expression, right? Remember that guy? So we kind of mentioned before, like, what's the future use of the app expression? The future use of the app expression is kind of applying a function to an input. Well, now we're specifying what the function is going to be, a diff function in this particular case. So we have this diff expression, or we have a zero expression. Okay, zero. So a diff expression takes in a minus, then takes in 2 expressions. A zero expression has the word zero question mark and then 1 expression. An if expression has the word if followed by an expression. Now, what kind of expression down the line do you expect that probably to be? It's not listed here yet. I'm kind of asking you to forward think. This isn't anything new. We've all seen if statements before. After the word if, what's the next piece? Like somebody gargled it, didn't they? Boolean. It's a Boolean expression. All right, so the next thing we should see is a Boolean expression. All right, so if some expression, which eventually will become a Boolean expression, then, so we're just throwing in the word then instead of an opening curly brace, whatever. We have an expression, else we have another expression. That's the true answer versus the false answer. What logic do we do? Okay. Otherwise, we have an identifier expression. That's a var expression, right? If I have an A, we need to go and resolve that variable to be some value associated with it. Otherwise, we have a let, where we're going to take a identifier, set it equal to some expression in, here's the body of it. All right, so let this variable name equal this value in this body of that let. Make sense? Okay. And like I said before, we're always going to ignore this type of data type implementation that they've kind of gone to in the book. 2 reasons. A, I don't like it anyways. And B, that makes you write it on your own instead of copying what's in the book. But I really don't like the data type thing. I just like the Lambda feel. I like having that language that's foreign enough to you that it actually makes your mind kind of start thinking more in the bigger scheme of the bigger scheme of programming languages, rather than get stuck in that rut where, oh, I like Java but not C#, or, you know, they're all the same. They're all the same. Hopefully we're starting to see that these languages, they all just have the same stuff. We just see them in a little bit different format. Okay. You know, and then they start getting into the stuff that's talking about the different kinds of values that we might have. And this ultimately has to do with our environment, and ultimately is going to revolve around this var expression, right? These are the kinds of values that these dudes can boil down to. Now, we do have a specific type built into the language called a const expression, which is always going to be a number. But this var expression allows us to expand our horizons on that, right? And say, oh, we can have different types that come out of a var expression. But now if we have that, we need a type inference engine to find out if we're allowed to use this type with this kind of input in this kind of function. And what did we call those guys? We called those guys, well, this would be an example, but previously we called it an app expression. Whether the functions were, the inputs are legal inputs for that guy. And then we've already talked about environments and different ways we can implement an environment, and this is pretty much consistent with that, with this idea of an extend D&D, with the main difference being, I don't know if they get to it in here, but potentially you could have multiple variables extended in a single environment, and then that allows us to start creating something called a scope. So that's where we're going with that. Okay. So then let's do this then for Wednesday. Do we have enough to write a parser for that? I think so. So I'm going to actually throw a little bit of a curveball in here for us, because since we're not using the data type here, it would actually be difficult for us, based on the tools we have, to write a parser that takes inputs that look like this. So that's more of a symbol-based input, like we're kind of used to with like Java, where you have a minus sign and we're applying that minus sign to the stuff inside the parentheses. Right now, the tools that we have work on lists. So something like this for our version of this language would be written like minus expression. That make sense? That makes it easier for us, more convenient for us. So now we're going from one list-based syntax into another list-based syntax, but we're going to be the one who write the interpreter, the ones who write the interpreter for it. The reason we're doing it this way is now we don't have to use the book's implementation of, they have kind of a built-in tokenizer that will go and pull out the minus and pull out the patterns inside here, ignore the comma, that kind of stuff. And we don't, with core scheme, we don't have those tools. So what I want you to write for Wednesday is a parser for that modified version of this language. All right, so the language from page 60, any place where they show a format like that, pull it all into a list and remove the comma. You know, give your alternate syntax for it. You could, if you want to get creative with it, that's fine. It's not going to make a difference in the final thing. Okay, this will be the function, the list containing 0 question mark, so on and so forth. This will be a list whose first element is an if, whose second element is a expression. You can keep the then out. You can omit the then, and then have expression followed by an expression. That's fine too. So write a parser for this guy. All right. Okay. I'll see everybody on Wednesday. Legitimate risk of a quiz on Wednesdays to keep people from skipping town early. So it's like the higher terror alert or something. We're on a